Okay, so this first video is going to look at speed, velocity and distance. We need to be able to have a look at what's called a distance time graph to see an object and how far it's gone, such as a remote control car moving away from us or a ball when we throw it. And those objects might move away from us, they might stay in the same place, or they might come back towards us. And that's what a distance time graph shows. So we've got two axes, time along the bottom and distance at the y-axis. And what it's showing us here, for example, from A to B, is that the distance from us is increasing. So the object, whether it's the car or the ball, is moving away from us. At the second point then, B to C, the distance isn't increasing or decreasing, so the object must be staying still, and then it starts to move away from us again before stopping once again. And then as the distance decreases between us and the object, it has to be coming back towards us. So if the slope is increasing, it's moving away. If there is no slope, it's stopped. And then if the slope is decreasing, then it's coming back towards us. Now there's a couple of problems with this. One of them is that this is only referring to an object if it's moving directly away from us. The object could be moving to the sides or round in a circle and so on, and this would not affect the distance away from us, but it would affect the distance that it's travelled. So this graph only shows you how far it is away from the starting point. Another useful thing to do with this is that it also tells us the speed. We can work out the speed because the slope of the line is the speed, or what we should say is the velocity. So if the gradient of the line, the slope of the line is sharper, then the velocity is greater, whereas if it's more gradual, the velocity is slower. That's because the equation speed is equal to distance over time gives us gives us speed, or distance or time. We can work out any one from them. Remember, speed is written in physics as velocity. And we can use this pyramid to work out any of these particular values when we're given two of the other ones. So here I've got distance is equal to speed over time. But what I can do is take out any one of those objects to find out what it is. So for instance, if I want to find out speed, I put the line through speed. That tells me speed is equal to distance over time, just like the equation says. On the other hand, I can put a line through distance, and now I can see that distance is equal to speed times time, or if I put a line through time, I know that time is equal to distance over speed. So if you're ever given two of those values and you have to work out the other one, this is a way to quickly rearrange the equation and be able to work things out. As well as distance time graphs, we've got velocity time graphs, and this one shows you a velocity time graph. So by here, again, we've got these similar shapes of a gradient increasing and decreasing and leveling off and so on, but they mean very different things. Because velocity is speed, when we're saying it's increasing, the speed of the velocity of the object is increasing, and therefore it's accelerating. So whereas the distance meant it was getting further away, the increase in this line means it's getting faster and it's accelerating. Another key mistake that people make is in this part by here B, where the line has no gradient. Because in the distance time graph it meant that the object is on stop, they assume it means the same thing here. But if it's simply that the speed is staying the same, it doesn't mean that the object is on stop. If I'm on the motorway driving constantly at 70 miles per hour, my velocity won't be increasing, it'll be staying the same. And as a result, on a velocity time graph, it would be leveled off. It's not that I'm going faster. And then finally, we've got this area by here where it's decreasing, and that means the object is deaccelerating. So we've got acceleration, the speed staying the same, and deacceleration. The gradient this time doesn't tell us velocity because this is obviously a velocity time graph. It tells us how much the acceleration is or how much the deaccelerating. So at the start, it's accelerating quite sharply. If it was a car, they'd be putting their foot down on the accelerator quite hard. They stay at constant speed, and then they brake the car more gradually. So they put their foot down on the brake a little bit softer than they put their foot on the acceleration. We can actually work out the distance that a car has travelled from a velocity time graph. So again, here we've got a velocity time graph. And to do it with a velocity time graph, we work out the surface area underneath. Now, to work out this surface area underneath, with the most difficult one, we use what we call the trapezium rule. And we split our velocity time graph up into trapeziums. So the first one by here is a rectangle rather than a trapezium, but all these then are trapeziums. And if you note, I've made sure that these trapeziums have got the same distance between the two lines. All are 2 units apart. You'll also note that some of them overlap the line slightly or underlap it. That doesn't matter as long as it's not too excessive, because this is an estimation of distance. Now, the area of a trapezium is half a plus b times the height, where a is the bottom, b is the top, and the height is the distance between the two. But on our graph, these trapeziums are on their side. So the area of each trapezium is half the first side plus the second side times the height, which is the distance between the two bars. So I can put these into my equation. The first one, excluding this area at the side, is 11 plus 6. So we've got half of 11 plus 6 times 2. The second one is half of 6 plus 3 times 2. The third one is half of 3 plus 2 times 2. And the final one is half of 2 plus 3 times 2. And then I can work these out to give myself the sum of 36 or 36 meters. So it's allowed me to calculate the distance from a velocity time graph. So let's have a look at some questions. Have a read of them and see if you can answer them. Pause the video and we'll go through the answers. So back now again, I hope. What is the answer to the first one? Well, what type of graph allows us to work out how far a car has travelled without using calculations? That's our first graph, the distance time graph. What's the formula for velocity without involving acceleration? So remember our speed, our velocity graph is speed equals distance over time, or velocity equals distance over time. What's the formula for time? So remember, when we rearrange that using that pyramid or triangle method, we change it to time is equal to distance over velocity. How do we work out the distance moved from a velocity time graph? Well, we need the area underneath the curve, and then the rule we can use to do that was the trapezium rule. And what is velocity over time a measure of? Well, that's acceleration, because the more we speed up over a given amount of time, the faster we're accelerating.